So, Dr. Afzal.
Hello, everyone. Yeah, Dr. Afzal.
How are you?
Good, fine. I'm fine.
Yes, nice to meet you,
Professor. Nice meeting you too.
Nice to meet
Professor.
you. Yeah.
Yeah.
So how we proceed the session? Do you have any idea?
Yeah, we can proceed the session. So, if you allow me. So.
Yeah. Yes, please. Yeah.
Yeah.
So may I record the time and questionnaire? So.
Yes, we need to. Yeah.
So please introduce the speaker, and I'll record the time. So their time 15 minutes, and I'll announce them. Yeah.
Yeah.
Also, I'll record some of the questionnaire from the audience here.
Yeah. Yeah.
Is this okay?
Yes. Yeah. Yeah. So the first of all, I welcome to all of you to attend this session, and Professor Home Rijal is with us, and the speakers for this session. So just as we decided that each presenter will speak for about 15 minutes, and the question and answer session will be at the end of all the presentations. So we have 4 presentations in this session, and then we will take the question and answers at the end of all the 4 presentations. So for those who are having some questions and comments, then they can post it through the question and answer chat box, or simply on the chat box, so that we can have a record of the questions, and then we can give these questions to the presenters at the end of all the sessions. So the presenters be with us till the end of the session, so that you can have the comments and the questions from different audiences. And yeah, this is from my side. So the first presenter is Mr. Abdullah Al-Nuaimi. So is he here with us? Oh, yeah, it
yes,
seems.
Hello, I'm
yeah,
here.
Thank you very much. So Professor Home, like with your permission, so we can allow Abdullah Al-Nuaimi to present his work. So you can share your presentation, and then you can start. Thank you very much.
So you can see. Yes, so do you see the screen, just to confirm?
Yes, it's visible to us.
Okay. All right, so today I'll be presenting my research titled Extreme Cold Discomfort in Extreme Hot Climates. So it's a case study of building overcooling in Qatar office buildings. This research has been done with me, Abdullah Naimi, alongside my supervisor, Dr. Suparna from the University of Bath. So just a few points about thermal comfort in Qatar. So Qatar
can you do the slideshow, please? Can you do slideshow? So
the full, or?
Yeah, full sliding.
Professor Home, the slides are visible. It's visible to us.
Yeah, now it's okay. Now it's okay.
Okay.
So just a few points about thermal comfort in Qatar. Qatar is a hot desert climate, an annual average temperature about 27.5 degrees Celsius. So this necessitates the use of active cooling within the building, more or less throughout the entirety of the year. About 55% of the total energy produced in Qatar is consumed by buildings, with 60% of that being the direct result of HVAC systems. Qatar currently does not specify local thermal comfort standards, as much of Gulf region is as well, and international standards are adopted. In fact, one of the leading global, or the green standards for Qatar, adopts ASHRAE 55 and the use of the PMB. Moreover, building overcooling. So overcooling is the excessive cooling in buildings that is caused by the purposeful expenditure of energy, which results in occupant cold discomfort. Overcooling is becoming more common occurrence in the sector across hot climates such as Qatar, and also the Gulf region. Early study done in 2012 in the US estimated the impact of overcooling to be about 103 gigawatt hours with about 50 kilotons of CO2 emissions and $10 billion in that year. So measuring overcooling, there's really two schools of thought in terms of assessing thermal comfort. So one is the subjective approach, which looks at thermal sensation vote, thermal preference votes, etc. The other is a calculated metric, or such as the PMV, which denotes comfort within a certain range based on that metric. So speaking about Qatar in general and the built environment in Qatar, so as a modern state, you can see that the typology is more or less alongside the international framework, where it's highly glazed office buildings. Anecdotally, some of the data I've collected in my field research hinted at overcooling, but this is a case for a more systematic approach into understanding what overcooling is in these environments. So you can see on the left side, you know, the occupants try to close the vents because they do feel overcold. They also maintain jackets in their offices whenever they feel cold. Some of the data I've collected in schools as well, you can see the students on the right-hand side, they leave the school wearing jackets, even though it's about 40 degrees outside. So to establish the effect of overcooling on cooling energy demand in typical offices in Qatar, we approached the methodology through 3 steps. Basically, first of all, is to estimate the extent of overcooling in Qatar through occupant responses. Second is to evaluate the comfort temperature set points that causes less cold discomfort, however, does not result in an increase in hot discomfort. And finally, we evaluate the reduction in cooling energy demand through the comfort temperature we have established, opposed to the observed temperatures we have collected. So the data collection was in about 6 buildings throughout Qatar over the span of about a year and a half. 2 public buildings and 4 private buildings. You can see they are semi-highly glazed multi-story office buildings. So for occupant data, the main focus in this research was looking at 4 questions that we've collected: the thermal sensation vote, the thermal preference vote, both on a 7-point scale, a question asking the occupants whether they felt too cold in that current climate indoors, and whether they are comfortable in that climate as well. Collecting the environmental data. So I used the SWEMA thermal comfort kit, which composes of a air humidity probe, a globe temperature, and an anemometer, as you can see in the setup to the right here, in accordance with the ISO 7730 standard. So this is the summary of the collected environmental parameters. Notably, you can see the main difference we found was a discrepancy in temperature from private buildings and public buildings, with about 2 degrees Celsius colder in public buildings, as there is an incentive, direct incentive in private buildings to reduce cooling because they directly pay for that energy, where everything in public buildings is more subsidized. So there isn't that direct incentive there. Also notably, we can see that clothing values in private buildings is a bit less than in public buildings, and this makes sense as public buildings and venues are more formally attired. However, when we aggregate these values within the binned indoor operative temperatures, looking at the question of, do you feel thermally comfortable? We can see that on average in colder temperatures, we have a high answer of no, which is about 68% in colder temperatures. On the other hand, in warmer indoor temperatures, you can see the average is a little bit below 20%. Likewise, when we look at the question of, do you feel too cold? We see that the average is about 72% in colder temperatures, where it drops down significantly. On the other hand, about 20% in a bit warmer indoor temperatures. Looking at the subjective metrics alongside with the calculated PMV, we can see that in public and private buildings, they're both cold compared to the PMV, which assumes they are slightly warmer. They will feel slightly warmer. However, in public buildings, it's a little bit more pronounced. So for my methodology for establishing what cold thermal discomfort is, i.e. overcooling, so I used the thermal sensation vote and the thermal preference vote coupled together to identify whether that occupant is really overcooled or not. So you can see in this example, if they're voting below a 1 in the thermal sensation vote and below a -1, on both the thermal sensation and thermal preference vote, that vote is considered that this occupant is overcooled. And that percentage is taken from the total study to establish the cold discomfort percentage, and likewise for the hot thermal discomfort. So when we look at the HD and CD percentages across a spectrum of bent indoor operative temperature, we can see that, so here we'll be looking at the blue. You can see that it is higher, about 47% when we look at the colder spectrum of temperature, where it's much lower than 20% when we look at the warmer spectrum. Likewise, we do not want to reduce cooling to the point where people feel hot, because if that's the case, then we're not really doing anything significant. But you can see hot discomfort hovers about 10% throughout the spectrum, 3, 6, 5, and so on. So this tells us that what we can see from this is, if we would set a temperature of 20, 21, or 22, we'd likely have discomfort, where 22 or 23, 24 would be less cold discomfort and equal hot discomfort. So maybe a more acceptable range for the occupants. So the next step for that is actually simulate the data in terms of, simulate our results in terms of energy use. So this is a standard prototype medium office buildings as it fell alongside with the floor area of the buildings we looked at. Typical construction, 3 floors and about 30% glazing are the most notable aspects. So when we simulate energy use for different set points on that model building, you can see in the red line, this is the annual cooling electricity demand for each temperature alongside the cold discomfort percentage. So at 20 degrees Celsius as a set point temperature, you can see about 72 kilowatt hours per meter squared is the energy demand, alongside with about 80% of cold discomfort. And whenever we get warmer, we can see that cold discomfort about 24 or 23 degrees as a set point is significantly lower, as well as the energy demand for that. So in conclusion, with rising global temperatures and human population growth, as well as warming and the mass adoption of air conditioning, this cooling energy demand is significantly due to rise in the coming future. Overcooling is an unnecessary use of energy, causing discomfort and energy waste. And we found in summary that increasing indoor set points by about 1 degree would result in about 8.5% reduction in cooling energy demand. Finally, utilizing appropriate indoor temperature set points in warm climates could increase occupant comfort as well as significantly reduce energy consumption. Thank you very much.
Okay, so thank you for your presentation. So,
Thank you.
So I'd like to introduce next presenter is Dr. Farhada Aloemi. So would you please start your presentation? Thermal comfort performance in a museum building in hot climates, Saudi Arabia example.
Thanks a lot to everybody. I would love just to take the chance to say thanks to everyone in this conference for being with all of you. I really enjoyed the material that my colleagues Abdullah present about the parametric design for the set points, at least the scenario that he did. Today we'll talk about the scenarios of designing museums. Both Oman and Saudi Arabia has great plans to to encourage this kind of buildings. So today we would like to put an example of examine this kind of buildings. So I would love just to take the chance to share the screen. Is that okay?
Yeah, please. It's yeah, now it's coming. Yeah.
Yes, just a minute.
So please do the full screen. Yeah.
All right. Is it now? Does it appear?
Yeah, it's good. Yeah. Yeah.
So my name is Fahad Al-Yami from Saudi Arabia, Imam Abdurrahman bin Faisal University. I'm really happy and glad to share with you the knowledge that we have, and we will share the experience of all of us. So the main task of this material will be mainly a background of the study and the methodology and kind of the results that I've done for the study. So first of all, the Saudi Arabia construction building field nowadays, as usual, it doesn't include the building envelopes, but in this kind of building, we would like to put them as parameters for the study, to examine them in early time, to check how this building will work efficiently in its life cycle. So the percentage of energy consumption in the government building sector reaches 20% in the late studies, and museums is part of this sector as of this reference. So this is one of our pavilions actually we did in the UAE, and it's really a great chance to invite you all to be part of this museum. It's really well designed, and we would like to share this experience with the worldwide through Expo as an example. Anyway, as a background, the orientation, there is no doubt that it's one of the main aspects that should be considered during design buildings, during design museums, not only for the people and the building itself, even for the exhibitions that inside the building, to protect them from the solar gain and the solar effect, and of course the thermal comfort for the occupants. So the climate and consolidation are two main measures of fabric design that's required in the consideration of design. The other thing actually is the path of the sun and how the building react as envelope, and roofings as well should react with the sun movement and the microclimate of this kind of area, which is Saudi Arabia as example, as extreme example of the hot country, like the other Gulf countries as well. So Mujib al-Shamrani tried to address the recent energy consumption and the recent actions to push a green sustainable solutions in this industry with about $26 billion. That's in 2016, and now this number is actually getting up with the recent initiatives of the Middle Eastern initiative by the Crown Prince Mohammed bin Salman. So they highlight that 26 billion has been invested over 76 green building projects. That was 5 years ago. Nowadays, this number is going up, as I mentioned. And you can see in the commercial part and the governmental, we are talking about 30% of the general energy consumption. And this will be one of the challenges to get a sustainable environmental design. So this study used the thermal comfort performance and relate to the energy consumption as a metric assess. And to check this prototype museum that's already addressed in the paper. So if anyone would like to take the details of it, you can check the paper as well. So it's a prototype museum that in the eastern part of Saudi Arabia during severe climate condition in summer. So it's actually a case in summer that's been tested for a designed museum just to check the possibility of the usage of the building in terms of thermal comfort, energy consumption, and the possible savings that can be done through this prototype design. So thermal comfort is defined actually by the ASHRAE or the nose as a mind of the expressed satisfaction of the thermal environment, and assessed by the subjective evaluation, which is delivered by the predicted mean vote and the people dissatisfaction percentage as well. And this leads to assess the expected consumed energy in order to provide the sufficient comfort level and at the same time the provided saving levels of energy. So we all know this scale of Banger, how we can measure the predicted mean vote, and what's the main consideration about the people as well, as starting from the clothing level, the activity level, till the surrounding microclimate conditions. This is the building that's been used as a prototype for this study. It's actually located in the east side of Saudi Arabia. It's 3 stories and has so many galleries, and we would like to check one of the zones of it to see how efficient in terms of built environment and namely thermal comfort and energy savings as well. So this is the scenarios that's been done, mainly in the envelope. As I mentioned earlier, the past practice on construction were not taking the building envelopes that seriously, but as we a hot country and facing the sun most of the time, of course, the envelope is actually one of the main key things that can dominate the energy consumption as well as the thermal comfort as well. So the base case was a plain case without any treatments. The second one, actually, it was a bit improved with some insulation, starting with polyethylene boards till the gypsum board, and the improved wall C. It's actually containing some layers in the middle of this envelope. So the part of the result of this study in terms of thermal comfort level for the scenario A, we're still getting something like 16% of people percentage dissatisfied, which is unacceptable based on the ASHRAE categorization of the dissatisfaction that should be not more than 15% in worst cases, that should be less than 10%, with 0.7 predictive mean vote result. In scenario B, these actually been decreased slightly to get 12% of people dissatisfied with 0.5 predictive mean vote, while in the last case, it's actually getting below the 10 degrees, which is in the acceptable limits with 7% of people dissatisfaction percentage and 0.35 predictive mean vote. In terms of the energy consumption savings, for the first scenario, you can see there is a big difference, about 8.3% of savings between A and B. And this actually getting slightly saved as well with the 9.5, we are talking about nearly 10%, with just only one parameter, only one, let's say, one parameter design that gave us something like 10%. So, as a conclusion, this paper describes the initial findings from a larger study that investigate a range of passive envelope interventions to reduce cooling loads. So this study actually is part of a longitudinal study. So we just gave you a part of it just to improve, just to prove that even a slight change in a building can lead to something. For this scenario, we get 10%. For more than cases, we can get something like 20 till 30. Till we get what we are aiming to have, a zero carbon building or a zero impact buildings to the environment. And this is actually the larger rationale of this study. Thank you. And I would like just to show you the latest pavilion that we have. It's called ITHRA. It's another invitation just to see, and you can see there is a big investment in this kind of buildings, and that is one of the main things that lead me to participate with all of you here, gentlemen. Thanks a lot, sir. I really appreciate this time, and I hope I'm keeping my time. Thanks, sir.
Okay, thank you very much for your nice presentation. So we'd like to move to the next presentation. The presenter is Eduardo Daismelado. Sorry, my wrong pronunciation. So the title is Thermal Comfort Assessment in Courtyard Under the Heat Waves in a Mediterranean Climate. So would you please start your presentation?
Okay, can you hear me?
Yeah, it's fine, yeah.
Okay, thank you. Okay. Could you see my share screen?
Yeah, it's good.
Yeah,
please
okay.
start it.
Okay.
Thank you, yeah.
Okay, thank you. Hello, everyone. My name is Eduardo Diz. I'm architect and researcher in the University of Seville. The title of my presentation is Thermal Comfort Assessment in Courtyard Under Heat Waves in a Mediterranean Climate. Sorry, okay. Did you know the importance of courtyard in the Mediterranean cities? Perfect. The main novelty of this research is the evaluation of the adaptive thermal comfort of courtyard as a function on the geometry. As you know, heat waves are becoming more and more frequent in Mediterranean cities, and this is influencing the health of the citizens. Previous research has demonstrated the temperature potential of courtyards, reaching thermal gap with the outdoor up to 15 Celsius degree. Some concepts have been taken account in the research, such as adaptive thermal comfort, courtyards, climate resilience, or sustainability. In this respect, that one we are developing actually, the project better, but benchmarking thermal behavior in transitional spaces as an energy efficient resource. This project is based on the premise of the microclimate potential of the courtyard in a current situation which effect on the energy efficiency of building is not taken account due to the lack of specific simulation tools. The methodology of the project analyzes the comfort in the courtyard objectively through different monitoring campaigns, testing different strategies such as thermal range, geometry, orientation, or other passive strategies such as shade, vegetation, etc. More subjectively, through adaptive comfort analysis. On the other hand, simulation tools will be used to analyze their influence on the interior of building. And in parallel, it is also intending to provide data through mathematical meta-analysis techniques. Focusing on the topic, there are two different standards to regulate indoor comfort, more restrictive than outdoor comfort indices, the European and American standard. However, previous research indicates that the calculation models of European standard could be better applied in semi-outdoor spaces such as courtyard. For this reason, this standard has been selected in this research. The European standard establishes several categories according to the user discomfort index for a metabolic rate between 1 to 1.3 MET and clothing insulation between 0.5 to 1 clo. The research was carried out in several regions of southern Spain. Several cities were selected in different climate zones, including coastal and non-coastal areas. According to the Köppen classification, the analysis regions belongs to CSA category with dry summers and rather warm temperature. In addition, summers are characterized by low rainfall. Furthermore, the climate zoning categorized by Spanish regulation is analysis for cities were selected, the cities of Mérida, Córdoba, Seville, and Cádiz. All the chosen locations were classified as a 3 or 4, the range of maximum summer severity with a very hot summer climate. A set of 20 different case studies of building with courtyard were selected for this research. This number of case studies is intended to demonstrate the thermal comfort of courtyard according to international standards. The selected case studies are mostly residential buildings, although there are some educational buildings due to the importance of courtyard in this type of building. The courtyard have the same characteristics in terms of orientation or albedo in the same urban environment with similar building densities. Previous research shows the influence of the aspect ratio on the flow pattern inside the courtyard. This makes it possible to assess the thermal comfort potential of the courtyard as a function of the geometry. Aspect ratio is defined as the ratio between the height and width of the courtyard. Aspect ratio 1 and 2 have been defined, one for each of the two main dimensions of the courtyard plan. The case studies have been divided according to the average aspect ratio range of each case study to check the influence of the geometry on the comfort capacity of the courtyard. The aspect ratio range are aspect ratio 0 to 1, 1 to 2, 2 to 3, and more than 3. The monitoring campaigns were conducted over 2 years to analyze the thermal performance of the 20 selected case studies. Following previous protocols, By other research, the minimum period was 2 weeks, recording data outside the building and inside the Goya. Outdoor weather data was recorded by placing portable weather station model PCE of the roof of the building. In addition, weather data provided by the Spanish Meteorological Agency was used to cross-check the data. Moreover, the thermal values inside the Goya were recorded by a Testo 174 sensors that allows placed at different levels to study the thermal stratification of the Goya. The data loggers were protected with radiation shields to minimize the overheating effect of the Earth's sun. Sensors were placed on the north-facing facade. Finally, for the analysis of thermal comfort, the operative temperature is required, so the mean radiant temperature has been monitored for its calculation. The result obtained from the monitoring campaign showed different possible analysis. Sorry. On the one hand, we can analyze the thermal gap between the outdoor and the Goya temperature, and on the other hand, the thermal stratification between the different levels of the Goya, or the diurnal thermal range between the outdoor and the Goya. The diurnal thermal range is the difference between the maximum and minimum temperature in a 24-hour cycle. The results are shown divided according to the average aspirative range of each case study to check the influence of the geometry on the comfort capacity of the Goya. The figure on the left shows the result for case studies 1 to 4 with the lowest aspirative. The results showed a dispersed behavior due to the higher influence of the outdoor temperature on this Goya geometry. Despite being the lowest aspirative, the Goya are in comfort 60% of the hours of the day. In the figure on the right, the case study with aspirative 1 to 2 are shown. Moreover, in the most representative aspirative of for Goya in Mediterranean cities, as I shown previous study, the result obtained is still so reaching 67% of the hours of the day in thermal comfort. The following range of aspirative 2 to 3, less representative than the rest, is shown below. In this case, the percentage of comfort hours in the Goya is 65%. In contrast, the figure on the right shows the case study with the highest aspirative and the best result in terms of thermal comfort, reaching 90% of the hours of the day in this case. If we look at all case studies simultaneously, the analysis of the result obtained shows the high heat tempering potential of the Goya. Depending on each geometry, the higher the aspirative, the better the Goya in terms of thermal comfort against high temperature. Finally, a case study is selected from each aspirative range. Specifically, the case study monitors the day with the highest outdoor temperature to analyze the adaptive thermal comfort according to the European standard in the warmest season. The selected case study were case study 4, 12, 13, and 19. The result showed that the Goya with aspirative below 1 are the least comfortable of the list of the selected Goya, with a percentage of daily hours in thermal comfort close to 70%. Moreover, in the aspirative 1 to 2, more than 75 of the hours of the day are between the limits of thermal comfort in terms of heating according to the European standard. The higher the aspirative range analyzed, the higher the percentage of comfort during extreme heat, reaching close to 90% in aspirative 2 to 3 and being in comfort 100% of the daytime hours in Goya with aspirative higher than 3, according to European standard. Finally, as a conclusion of the research, the results show the temperature potential of Goya being rooms in thermal comfort during many hours of the day. In addition, the influence of the geometry of the Goya is very important in terms of their temperature potential and comfort. The most common geometries of Goya in Mediterranean cities are found to be in comfort for more than 80% of the hours of the day. Here you can see some reference used in the research, And that's all. Thank you very much for your attention. Sorry.
Okay, thank you very much for your presentation. So we'll have question and answer later.
Perfect. Thank you very much.
Okay, for the last presentation in this session, I would like to invite Professor Hom Rijal. So he will be presenting on thermal environment and thermal comfort for Nepalese dwellings in extreme cold climate. So it's the Nepal, about the country Nepal. So it's a bit different from the other three presentations in the sense like the previous presentations, they talk about the comfort, especially in the hot regions. And it seems that the last presentation is talking about the extreme cold climates. So it's a contrast difference between the other presenters. So Professor Hom Rijal, so have the floor now. Thank you very much.
Okay, thank you very much. So can you listen me, right? It's okay, right?
Yes, yes.
Yeah, okay. So I'd like to start my presentation. So my title is Thermal Adaptation, Thermal Environment and the Thermal Comfort of the Nepalese Dwelling in Extremely Cold Climate. So as you know, we have a two pole. So one is the North Pole and another is South Pole. So last time when I was talking with Professor Suro, and she was telling to me, we also have another pole. So it means third pole. So maybe this is the Himalayan pole. So it means we have a very high altitude, and that's why we can have a very different climate. Just a moment. Setting. So that's why we have a very different climate, which is very extremely cold, especially in the winter. So in Nepal, so in the extremely cold climate, so actually the building is designed, so which is matched to the climate, also sometime with the culture. So basically in the cold climate, so they have a flat roof and also sometimes very thick wall. And also the window is quite a small size, and sometimes they also have a courtyard, and also all the houses is connected each other, and it looks like a very compact. So, however, in this climate, not many research has been conducted. So, in terms of the thermal adaptation of the people, so because of the high altitude. So we have a very low outdoor temperature and sometimes very high wind velocity. So that's why maybe the sensory temperature is very low, and people are wearing the heavy clothing. And also because of higher altitudes, the firewood is not much available, and the people burn livestock dongs. Thermal, but however, the thermal adaptation of the people is very important in this climate. So we have been doing research in the various part of the Nepal. As you see here, some is the low altitude and still some is a high in a different season. But actually, the research which I'm focusing is the altitude is very high. So we didn't have that kind of research. So how the people is adapted in the high altitude, it's still we need to do more research. So really this study is how they enjoy thermal environments and how the people is satisfied in that environment, and also their comfort temperature, and how the comfort temperature and the thermal environment is related, and to show the potential of the energy saving. So this is the study area. So Nepal is a very small country. So southern part we have a subtropical, and this is temperate, and in northern part we have a cold climate. The distance is about 200 kilometers. So in this 200 kilometer, we have many different climate we can have. And this Mustang area is near to the Tibetan border, and which has about 3,700 meters. So from the sea level, so it's very high altitude, which I'm focusing in this study. So the Mustang, which has a very high altitude. So as you see here, and the temperature, the monthly mean temperature is a low. So it goes, mean is below 0 degrees C. And when I measure the temperature, it goes to minus 10 degrees C. Sometimes it goes to minus 20 degrees C, so very low. And also the rainfall, also we have not much rainfall in that area because it's the northern part of the Himalayan region. So as you see here, we can have this kind of building. So in the Lomantang, so it has a very cold climate. And also this is some of the photograph which we took a measurement. This is for the outdoor and this is for the indoor environment. So we have a measure different variable, solar radiation and temperature, wind velocity. And this is the houses for which we did a thermal comfort survey. Also, we have done some of the measurement. And this is the people for the thermal comfort survey. As you see here, so they are wearing a very, very heavy clothing, very, very heavy clothing to adapt in that very cold climate. So you see here, the clothing insulation is quite high, and you can see some of the picture for the indoor measurement. So this one, so basically I'll talk about the thermal sensation. So we have used a 9-point scale, and that is overall comfort, and we also ask them their preference, thermal preference. So the survey is conducted in the 4 days to the 35 people, and only daytime. We have collected data each hour, and the condition is resting, and sometimes they are doing the housework. And then we have collected more than 1,500 data, and we also measure the weight of the clothing, and from that weight we calculate in the clo value. So I like to explain about the thermal environment, so of the dwelling, how the dwelling in that particular area. So at first I want to talk the outdoor environment and the building design. So this is the solar radiation, and this is the wind velocity and the wind direction. As you see here, the Nepal is a very low latitude. That's why we have a very high solar radiation. Also, due to the high altitude, the wind velocity is also quite high in the daytime. So the balcony and the courtyard, as you see here, are found to obtain the maximum solar radiation, and the small window and the building is connected are found to avoid the cold wind. Then I want to explain about the variation of indoor temperature in the heated room and the non-heated room. So this is the by time. As you see here, this is the outdoor temperature and this is the indoor temperature. During the daytime, when the room is heated, so it goes to up to 25, around 20 degrees C. But in the non-heated room, the temperature is below 5 degrees C. So it's a heated room and non-heated room. The temperature is very, very different. Then I try to compare this temperature because it's a very low temperature. It's a very surprising how the people stay in such a low temperature. Then when I try to compare with the other studies in Nepal and also some in India and China. So as you see here, especially in a Chinese dwelling, they also have a quite low temperature. So it means the case in Nepal and some of the Chinese dwelling, so we can have a very similar indoor environment. Then I try to compare the air temperature difference between the horizontal differences and vertical differences for the heated room. So this is the horizontal means, so around the stove and also in trans. Vertical means ceiling and the floor level. So as I explained previously, in the daytime, they have a quite high vertical differences and also horizontal differences. So it means because of the temperature differences, so maybe sometime we can say they are wasting some of the energy, and maybe they are not properly. Sometimes they open the door and windows, then the temperature difference is very high because of that reason. And I try to look the thermal performance of the building. So the in terms of the roof. So as you see here, so this is the outdoor temperature and the temperature of the ceiling and the temperature of the roof outside. So as you see here, from outside and the inside, the difference is very, very high because the ceiling is very, very thick. So that's why maybe this mud is made by the mud which might be the effective as an insulating material. So next section, I'd like to talk about the thermal comfort because of the residents. So as I explained, they have a very, very low indoor temperature, and how the people finding thermal comfort in such a low indoor air temperature. So this is the thermal sensation. So you can see the scale here. So if we take a -1 to 1, I mean slightly cool to slightly warm, so you see that more than 60%. And that this house is low, but these two houses is quite high. So maybe it's maybe we can say generally not very discomfort. Maybe the comfort level is not very bad, I can say. So I think the people is well adapted to that climate and they are satisfied with the thermal condition of the traditional houses. Then I try to compare the comfort temperature and the indoor temperature in the three different houses. So the comfort temperature is we have calculated by the Griffiths method. So this is the comfort temperature, this three, and this is the globe temperature, the measure. So as you see here, if the globe temperature is low, the comfort temperature is also low. If the globe temperature is high, the comfort temperature is also high. So even in the same area, so the temperature, the indoor temperature and the comfort temperature is quite different. So generally about, this one is about 8.5 degrees C generally, and this is maybe about 13 degrees C. Generally, if you take a mean about 10 degrees C, 10.7 degrees C is okay for this climate. So this is very low. The temperature is very low. Maybe you're surprised to have such a low comfort temperature. Then I try to compare with the other studies. So in the Nepal and also India and China. So as you see here, some of in the Chinese dwelling, so you can find the band. So lower limit and upper limit is quite low. Also, some of the other Nepalese dwelling also is lower and upper limit is quite low. So it means not only this Nepalese climate, but also other climate, we can have a similar comfort temperature. Then we try to look the how the indoor globe temperature and the comfort temperature is related. So this is a scatter plot. So as you see here, if the globe temperature the people experiencing is low, their comfort is also low. If they have a high globe temperature, also they have a high comfort temperature. So it means what temperature they are living, that temperature is also affected the comfort temperature. As the final section, I like to explain about the potential for the energy saving. So you see they have used this kind of the lifestyle dome and also serve because they have a very, very limited firewood because of the high altitude. So how the energy saving potential, so which I want to explain. So this is just based on the literature review, and actually I tried to analyze more, but I didn't have enough time. So I just tried, for example, based on the literature review, for example, if you have a 1 degree C temperature setting, if you change, that would be equivalent to the 10% of the energy. So for example, in Japan, China, and also UK, and they are giving this kind of the value. So if we consider the low comfort temperature, as we explained in this study area, people are saving a significant amount of energy. So for example, if the other area, if they are maintaining 20 degrees C, if that Mustang area, if they are maintaining 10 degrees C, maybe 12 degrees C, so it's a -8, isn't it? So it means almost 80% of energy is saving in compared to the other areas. So using the various thermal adaptation. So conclusion, so I want to say basically this thing. So passive heating effect are found in the dwelling for keeping warm. And also residents are satisfied with the thermal conditions, and the comfort temperature is low, and thus they are saving a large amount of energy. So the thermal adaptation of the building and also the people are important. There's a resilient thermal comfort. So this is the book. If you want to know more about the resilient thermal comfort. So the book will be published in the next year in the April. So we have our 34th chapter, 91 authors from the 20 different countries. We have 210 figures and about 100 tables and 250,000 words, and it will be the 616 page. So if you are interested, so maybe you can find more information here. So that's all from my side. So thank you very much.
Thank you very much, Professor Home Rijal. So here we end up the presentations, and now the floor is open for the question and answers and discussion. So I will take the questions from your chat session. So me and Professor Rijal together will take the read the questions, and probably the presenters they can answer the questions. So the first question, it is from that came coming. Okay. It is to Dr. Abdullah, who presented the paper, and it says that, I mean, I don't know, Dr. Abdullah, if you can read the question from the question and answer session.
Yeah, sure.
This is the first question. First question by Sue Roth.
Yes.
This to you, like it seems that the people would be happy in building with 26 degrees Celsius indoor, what they might really like to do. Yeah, if you can answer this question.
Definitely, yes. So yes, I do agree with Professor Sue. And this is something I found in my research, extended research. Even 28 degrees Celsius sometimes is comfortable. And I actually found that this is generational. You know, the generation before me would set it to 26 and they would still be cold, where the newer generation starts to set it at 20. But I think it also goes along with the second comment. Professor Sue says that the international standards or the PMV were developed in slightly cooler regions and maybe not applicable in hot climates. And this is something we find more in public buildings where they're basically, you know, publicly funded, so they adhere to high standards and international codes. And that's the result of the overcooling that we find. It's less of a problem in public buildings. And then also windows sometimes is a tricky question in the Gulf. There's a lot of dust, so that would be something that has to be addressed, is how to open windows without allowing the dust in. But I agree, it is the future. Smart controlled buildings with personal control, yeah.
Okay, thank you very much, Dr. Abdullah. Another question, I mean, it's sort of a kind of comment, you can say, like how to convince the property managers to increase thermoset points during summer while maintaining thermal comfort. So
yes, this is from Haytham. Yeah, so in private buildings, there is the direct incentive there because they're saving money. They have to pay for their electricity. So they set it to the point where, you know, the occupants are not complaining that they're hot. So in private buildings, I found that average was like 25, 24 degrees Celsius, where, you know, the property manager was happy and the occupants were happy. However, in public buildings, again, there's no incentive because this is subsidized. They just set it to whatever the standard is. And then the issue is people actually, the occupants result in heating themselves by either overclothing. You know, there are extreme cases where people bring heaters and turn them on. Some people, like, they take 10-minute breaks every now and then just to heat themselves. And it's the way they set it is they set the coldest temperature to provide comfort for people who complain for hot, and then the people that are cold should heat themselves actively or passively. Where I believe the approach might be, you know, to set a minimum cooling and then augment whatever extra cooling people want through a personal comfort system. So if somebody wants to be really cold, he could just turn on a fan instead of forcing everybody to be cold and keep them warmer. So that's pretty much a work in progress, Haytham, and I think it's a good point. Thank you. And I think there's just one more by Nishan, I believe, for clothing. I can address that right now. So they're asking if clothing constraints to student due to religions in school. So in school specifically, there are uniforms that are specified by the school itself. However, in this study, I was looking more at offices, but this is, it was talking about the anecdotal evidence for overcooling in Qatar. Surprising fact in terms of clothing actually is jackets in offices. So there's no requirement for jackets, but people are actually putting on jackets because they're cold. And part of it is cultural too, where, you know, in public buildings, we found slightly greater clothing values because there are visitors, there are people who come, you know, to either, these are public buildings, so there are people that are coming to finish their work and stuff. So they had to dress a little bit more cultural, something along the lines of what I'm wearing. How do you see the attitude? So just a question popped up now from Dr. Madavi saying there's great reluctance to use fans in higher air movement. How do you see that? So yes, I think me and her work along in the same field and understand that this is an issue. I believe that, you know, in terms of an energy conservation perspective, it's better to set the lowest and then augment whatever cooling you need instead of setting the top and then forcing people to be uncomfortable. It comes down to conservation, whether they want to conserve or not, and take the measures. Thank you.
thank you very much, Dr. Abdullah, for your responses. And so the questions to the next presenter, Dr. Fahad. So the first question is from Dr. Su, that are you concerned in building resilience into your buildings, which requires that windows can open when, for instance, the power grid fails? So if you can read that question in the question and answer chat box.
Yeah, I've checked them, sir, and I really appreciate that from Dr. Su. I would like just to say hi to her. I've got your email, by the way, and I know the person they asked me about. Actually, Professor Su, she asked me so many things, to be honest, even in the email. Yes, I'm interested about the building resilience in my buildings, but not really about the buildings that can be openable windows. I'm interested about static buildings, to be honest, something closed, sealed according to the hot climate. About the second part, or maybe the second question, which is regarding to the predicted mean volt scale. I do believe this could be applicable even in the hot countries, just to measure the neutral level or the comfort zone for the occupants. I would take the chance to take your advice about reading that book that you sent to me. I really appreciate that, Sue, and I hope I answered the questions. That's for you, Sana.
Thank you very much, Dr. Fahad. So I think that's the question for you. And the next, I can see the question for Eduardo. If you can see the chat, then there is a question for you. And And that is about like, given your research results, can thermal comfort improve further with simply installing vertical or horizontal shades on top of the courtyard? So
Yes, it's a good question. Of course, comfort could be improved by applying different strategies on the courtyard. We are testing now different shade strategies, or installing green facade, or applying different nebulizers on the courtyard with really good results. In terms of comfort, we have recently published in Building and Environment analyzing the thermal comfort according to the European and American standards in summer and in a heat wave season, and the results are even better in this case. So it's very, very interesting, apply different shade or other passive strategies in Korea with a very good result. Thank you very much for the question.
Another question is from my side, Eduardo. Like you said that the aspect ratio is an important parameter for the thermal comfort, especially when we talk about the courtyard. So what other parameters do you think that one should take into consideration when there is a construction of courtyard? Any suggestion?
Okay, then there are two very important parameters. One of them is the aspect ratio, the geometry in general, and the other parameter is the outdoor temperature. When the outdoor temperature is high, the thermal gap in the courtyard against the outdoor thermal is very, very better. And the aspect ratio is also the other important parameters. There are also different parameters important, like the presence of vegetation or water, and then the constructive characteristic of the build. We are analyzing a courtyard with different albedo, for example, and testing the result in terms of tempering potential the courtyard against the outdoor climate.
Thank you very much, Eduardo. Another
Thank you very much.
late question. So if Dr. Fahad is still with us, there is another question from M. Indraganti for you. Dr. Fahad, if you are still with us, your mic is, yeah, there is a question in the chat box, like how about allowing windows to be openable for the cooler seasons, or leave the windows operation to the occupants?
This question could be delivered for any other kinds of buildings, not the museums, to be honest.
Mm-hmm.
But if I put the winter season as one of my considerations in any other studies, this one would be a good argument that could be discussed and researched. So it wasn't one of my parameters in this study, to be honest. Windows, just in terms of the security of the building and the type of the building itself. It's a museum. If that's, let's say it's a school, that will be a different matter.
Thank you very much, Dr. Fahad. Thank you very much.
May I ask one question to the Eduardo?
Yes, okay? Please. Yes, please.
Yeah. So I think you have. Are you listening, Eduardo?
Yeah. Sorry.
Yeah.
Sorry.
So I think you use a European standard to compare your result, right?
Yeah.
So that is, I think, is based on the office building, but you are plotting the data of the courtyard, isn't it? So
yes,
the result, the indoor and the courtyard, the perception and the temperature could be very different. So that might be the some of the data is below the band, isn't it? So that one, I think you need to be careful. I just felt. And another one is I'm not charts here, so when the temperature is high, you have a very straight band, but actually the European standard is going up continuously.
Yeah.
So
Yeah.
I don't know, you have a different standard for that one, or but
Yeah.
in the original standard they don't have that flat for the high temperature.
Okay.
Hmm.
Okay. Okay. In the first question, we analyzed firstly three different possible to analyze the thermal comfort in Koya. The first one was the European standard. The second one, the American standard, as right. And the third one was use the outdoor comfort index, like CATE. And in this research, we analyzed that the best result was the European standard result. Actually, we are not an index to analyze the comfort in semi-outdoor spaces like a Koya. And this research I can write now in the chat the paper. We analyze the thermal comfort in two different Koya with a normal geometry with a very good result. The result in European and the outdoor index were very similar, and the American standard was more different result in this case. So we decide that the best standard to analyze the thermal comfort in Koya in this case was the European standard with the normalest result. And the second one question, yes, the figure of the European standard is until 20 or 23 Celsius degree, I think. So
33, I think it goes to up to
yeah,
33 degree. Yeah.
Yes. So to limit the result, we decide to mount horizontal the line to be in the security state. If we continue the line oblique, we could be a false result because we could be more temperature in the Koya when the outdoor temperature is highest. So we decide put in this case the graphic horizontal in this research that I was commenting before. You can revise in this investigation. I don't know if I have as well the question. Very good.
Yeah, thank you very much. Yeah.
Okay.
I don't know, I forgot, but some of the, I think Netherlands or some of the standard, they made a flat, I think. Maybe in the upper limit, they just made a flat, not going continuously increase. I think maybe you also maybe refer that one, I think.
Okay.
Okay. Thank you very much. Yeah.
Thank you very much.
Thank you, Eduardo.
Thank you.
Yeah, so the next will take questions for I see the question, but I do not know exactly to whom it is addressed. Like the PMV is over predicting to the tune of 3 volts, more so at warmer and colder side of the sensation scale. Because it is not mentioned in the question to whom it is.
I think this is the second presentation. So in museum, so he used PMB as to evaluate the space. So,
okay.
Maybe second presentation.
So I don't know if Dr. Fahad wants to answer this question. Okay, so then we can move. Yes, Dr. Fahad, please.
What was the question, please?
There is a question in the question and answer chats. The PMV is over predicting to the tune of 3 volts. So more so at warmer and colder side of the sensation scale. I mean, it's comment is a sort of comment.
I guess I answered this before. I think.
Yeah. Okay. Thank you very much,
Yeah, I answered.
Dr. Fahd. Thank you very much.
Oh,
Yeah.
you're welcome.
So next we move to the question, which is from Dr. Su to Professor Holm, that the human beings are like thermal batteries, and when they go to work outside, the heat drops down, and so they come back in and sit by the fire to top us their thermal battery and then go out again. So we found that out from Dolana's study of Siberian nomads. So Professor Holm, you may comment on this. I mean, it's a sort of comment here.
Yeah, thank you very much. So it's very interesting. So maybe we need a more observation. Yeah, it's really very interesting comment. Thank you very much.
Thank you very
I
much,
agree with you. Yeah.
Professor Holm. And there are some more questions for you in this.
Yeah, so first one from the Sue. So I fully agree. So with you. So in extremely hot climate and extremely cold climate, so really the window size is very small, and also the wall thickness is very high. I think that's the how the traditional vernacular building is they're doing. So I think so. I'm also very agree with you. And another comment or question from the so is also so for the flat roof. So the region is the area which I was doing survey. That area is the rainfall is very small amount of rainfall, because it's a shadow of the Himalayan region. All the monsoon is a block by the high Himalayan. So it's over 8,000 meters. So it's all the rainfall in the southern part of the Himalaya, and the region which I'm taking is doing is northern part of the Himalaya. So that's why because of that region they made a flat roof, and that area also have a snow, but because of the low latitude, so the snow is only maybe a few months, not in the many months. That's why, because of the issue of the rainfall, they may have made the flat roof.
Thank you very much, Professor Holm.
Yeah, thank you very much.
Yeah, please take another question here.
Yeah, I think that's all, isn't it? Yeah.
Okay. So another, the question is from my side. I mean, it's a general question because these are very interesting presentations, and just because my background is a mechanical engineer, and we usually design the machines behind the cooling system. So like in general question, like anybody can comment on it. Like we usually like talking about the overcooling of the buildings. So what are the reasons of like overcooling the buildings? I mean, why can't we just cool the building to its required level? I mean, why is there overcooling? I mean, any reason? Like, I mean, if anyone can comment on
Hello,
it. Yeah.
I think
Yeah, thank you very much.
More to me. So there have been research talking about elements of overcooling in hot climates, and specifically in humid climates where most of the cooling is to actually dehumidify. However, an approach I did in a previous research was actually looking at big budget buildings, public buildings versus more private buildings, and maybe smaller scale HVAC systems. So like package systems. It is possible at lower or higher temperatures. There are points where people feel comfortable. It's not the issue. I don't think it's the issue of the mechanical system itself. I think it's more of the issue of the setting or the set points of those mechanical systems. Since some of the researchers here commented, and Professor Su also mentioned that, if you're using the PMB to assume temperatures for your occupants, it's going to be, predicting slightly warmer, therefore overcooling the occupants that are there. So I think there has been evidence for, for that. And one of it might be, low flow systems where it's not blasting air or something, or more individual personal systems. So I think it's not the issue with the mechanics more than the issue of regulations and recommendations, I think, or understanding the local cultures and tradition there in terms of the people and what's suitable to them. And this is why adaptive comfort is in the field as well.
Yeah, thank you very much, Dr. Abdullah. Thank you.
Yes.
So I think
Actually, I have one question from Madhavi, so I haven't answered her. So Madhavi, thank you very much for your question. Yeah, so really, they have a very, very thick clothing and very, very heavy. So when I measure the weight of the cloth, so they have sometimes 5 kilo, 6 kilo, even sometimes they have 7 kilo of clothing they are wearing. So maybe for us, maybe it's very difficult to imagine to wear such a heavy clothing. But I think, of course, maybe they have some difficulties. It's not easy to do some housework, but they have that maybe a kind of the culture, so which they are living. Also, you see the temperature is very, very low, and the people, they are not taking the bath very often, and sometimes they have sometimes the smell also they have. So for us, so maybe, yeah, the temperature, so 10 degree might be, or 8 degree might be quite low for them, but if we have if the society modernize, and also, and if they can have access the energy easily, maybe they may change their behavior and also clothing style, which is suitable to the modern lifestyle. Thank you very much.
Okay, so with this, we reached to the time allocated for this session. So I would like to thank everyone, and especially for the presenters and those who put this session into an interactive one by putting some very pertinent questions to the presenters and participated in the discussion. Thank you very much to all of you once again. So by this, if Professor Holm has anything to say, and then we can end this session.
Yeah, thank you very much. Yeah.
Thank you very much for all. Assalamu alaikum.
Okay. Goodbye. See you later. Bye.